Okay, hi there. This is Dr. Matthew J. Traum, and this is the first fluids refresher. In this one, I'm going to talk about the definition of a continuum fluid, and I'm going to try to motivate why the Navier-Stokes equations cannot be solved. And let me just say that this particular video doesn't really have any technical content. It's more of kind of a preview, a precursor to explain and justify kind of where we're going. So future fluids refresher videos are going to talk about things like hydrostatics, Bernoulli's equations, special solutions to Navier-Stokes equations, Reynolds transport theorem, and so forth. So things that are useful, but it's important to kind of lay some foundational groundwork so we're all on the same page with respect to what we're talking about and what tools we can use to solve engineering fluid mechanics problems. So this is the first of a series of these videos. Okay, so first slide. What is a continuum fluid? Well, I'm going to start by saying that happily in the design course, we are probably not going to end up dealing with systems that are small enough that the fluid involved becomes a non-continuum fluid. So the continuum fluid is an assumption that we make right at the beginning of an undergraduate fluid mechanics class. And you guys will be able to make that same assumption here. Places where the continuum fluid assumption breaks down are situations where you either get really really small or you have fluid that is incredibly diffuse, so has really really low density. So for our purposes, none of the oils or waters or gases that we're going to deal with kind of violate those conditions. So that's good, because all of the tools that you guys learned in your undergraduate fluid mechanics class, for the most part, assume that you're dealing with a continuum fluid, like water at room temperature or pressure, or air at standard temperature and pressure, for example. Those are both continuum fluids. So what is a continuum fluid? Why is it important, and why even bringing it up? Well, the importance of a continuum fluid, I think, really is best expressed by kind of understanding why fluid mechanical and thermodynamic properties are the way they are. And the underlying assumption for all of these properties is that you're looking at a homogeneous fluid, which means it's basically the same everywhere that you look at it in space. And it's a fluid where you do not see the individual behavior of the particles themselves. You see sort of the average statistical behavior of all the particles acting together in aggregate. So the best way I think to describe this is to just give you an example, which is the fluid mechanical property of density. So here I've got density. And a standard definition of density is just a mass over a volume. So I can also say that it's just a differential mass over a differential volume. And what that does is just allow me to change the size scale of interest that I'm looking at. And I'm going to use this to kind of show you where this breaks down, where density stops making sense, and therefore a size scale at which the continuum fluid assumption also breaks down. So one way to kind of think about density, and what you're usually told in a fluids book, is that you just can take the limit as the differential volume goes to zero, and density is density, and it doesn't matter how small your field of view gets, the property of density is always the same. Well, in reality, that's not true, because in real fluids are made up of particles, right? Molecules and atoms. And the fluid behavior that we get is a result of those atoms and molecules interacting with each other and moving around each other and so forth. And so it turns out that if you shrink this delta volume, this volume of interest, down small enough, you get to a point where you're not looking at collection of particles. You're looking at just some particles, maybe one particle, heck, maybe even no particles if your volume is small enough, and all of a sudden this concept of density doesn't make sense anymore. And so that's sort of where this continuum fluid breaks down. And so we use delta V star. V star is the volume at which the continuum fluid assumption kind of stops functioning, stops working correctly. And so the way of I think best thinking about that is this kind of sequence of kind of fluid diagrams that I've got here. So I've got A, B, C, and D, and these are all meant to be the same fluid, except A is looking at the fluid with a lot of like microscopically, right? So I'm looking down at the fluid with a lot of zoom, and B is I'm looking at it from slightly farther away. C is even further away, and then D, I'm looking at it from a perspective that I can't see any of the individual particles. So each one of these red balls is meant to represent a fluid particle, and as your microscopic zoom value goes down, right? So I'm looking here very close to the fluid. Here I'm looking a little bit farther away, even further away, and here the zoom is completely turned off. You lose your ability to see the individual particles, and the fluid becomes more and more and more like a continuum fluid because the individual behavior and the individual identity of those particles disappears as you look farther and farther away. So to think about this concept of density, I've drawn kind of two boxes on each of these different kind of particle representations. So there's the yellow box, which I've intentionally placed right in the middle of the fluid, and then there's the green box, which I've intentionally offset by just a little bit from the yellow box. Now, the green box and the yellow box are meant to be the same size. The only thing I've done is just move the box from its position as the yellow box to its new position as the green box. To illustrate the point that I'm trying to make. So if you look at A here, right, I'm zoomed way in on this fluid, and I'm actually seeing 4 individual particles kind of in my microscopic view. And then if I take a region of interest, so this is like a delta volume of interest, I'm capturing maybe like a quarter of each of the particles, right? So if I were to calculate the volume of this region, it might be 1 particle divided by the volume of the yellow box. But now, if I take the yellow box and I move it, if I offset it to the location of the green box, remember that delta volume is the same size. I haven't changed the size of the volume that I'm looking at, but I've now captured more particle and less of this void space, right? So it actually appears as if the density goes up, right? Because I've now got more mass in my box of the same size for the green box than I had with the yellow box. And the closer I zoom in, the worse that problem gets, right? So I don't have a constant value of density depending on where I put the green box and the yellow box in this zoomed in version of the fluid. If I now move over to B, I've got a slightly less zoomed in version of the fluid. I'm looking at more of those fluid particles, and now in my yellow box, I've captured, nominally 4 particles in this volume. But then if I move the box from its yellow location to its green location, again, I'm looking close enough that the number of total particles that I've captured, the total mass in that green box is going to be different than the mass in the yellow box. And if I try to calculate the density, given that those boxes are the same volume, I'm going to get 2 different densities just depending on where I'm looking in the fluid, right? So still, I can't assume that this is a continuum fluid because I'm still seeing the individual influence of the particles and the spacing between them. So now let's move to C, right? The situation is getting a bit better here. So I'm still seeing the individual particles, but now I'm zoomed out enough that I'm seeing an awful lot of them in my yellow volume. So I'd argue here that if I move from the yellow volume to the green volume, I'm pretty close to having captured the same amount of mass in both of these squares, even though one is offset in space from the other one, right? Because again, now I'm zoomed out far enough, those particles are small enough, I've got enough of them in my box that moving the box doesn't really change the answer all that much. And then D, this is now my continuum fluid, right? I'm zoomed out so far that I cannot see the individual particles at all. And now it doesn't matter. I can move the box anywhere I want. The yellow box, the green box, it doesn't matter where they are. So long as they're the same volume, I'm nominally capturing the same number of particles. And so my density is going to be the same regardless of where I look in the fluid. So the transition from C to D, I'm going from a non-continuum fluid in C to a continuum fluid in D, and that threshold occurs at delta V star, which is somewhere on the order of about 10 to the minus ninth cubic millimeters, right? So you can see this chart here. I've got density on the y-axis, I've got my volume, delta volume on the x-axis, and as I'm increasing the size of that volume, that's basically the equivalent of looking at these kind of different size scales, right? So A, B, C, and D. One way of looking at it is, okay, I'm zooming my microscope. The other way of looking at it is I'm just increasing the volume of interest that I'm interrogating with my little capture region here, right? So this is a very small capture region. This is a bigger capture region. This is a bigger one, and this is yet an even bigger one. So it's possible to look at these pictures that way as well. And so what you can see is when I'm down below this limit of delta V star, my density just jumps all over the place, right? First it's high, then I move the square a little bit, and then it's low, and then I move the square a little bit, and it's high again. It doesn't make any sense. It's a non-continuous function until I reach that threshold of 10 to the ninth cubic millimeters, and that's when all of a sudden I'm in my continuum fluid regime. So that's just effectively what this means. And again, all the fluids that we're going to deal with in this class are continuum fluids, but it's important to know that there is this situation out there, especially if you start dealing with MEMS fluids or nanofluids, where the continuum fluid model breaks down and you cannot use just the standard equations. The first thing to go is probably the need to deal with surface tension, right? So surface tension effects happen at kind of a millimeter scale, so you have to start worrying about those when you have fluids that are about a millimeter in scale. And then after that, the no slip condition goes away, and that's fluids that are sort of on the micron scale that you have to worry about. Okay, so having kind of beaten this one to death, let's move on to the Navier-Stokes equations. So these are the Navier-Stokes equations, and they fully define the motion, all of the forces acting on a fluid, and just like using F equals ma, if you solve for all of the forces acting on the fluid, you can figure out how the fluid moves. And so, hallelujah, this should be the solution to every fluids problem, is just to solve the Navier-Stokes equations for that particular configuration. What's the problem here? Well, the Navier-Stokes equations are all very complicated, three-dimensional, nonlinear differential equations that in most cases cannot be solved simultaneously to a closed-form analytical solution. So in other words, we know what the equations are, but we cannot solve them. And because we cannot solve them, fluid mechanics is actually an engineering field and not a physics discipline. If we could solve these equations, fluids would be physics, right? Because you could actually get a closed form analytical solution for any problem, no matter how complicated it was given to you. And so therefore it's a scientific fact, and it's science rather than engineering. The entire discipline of fluid mechanics arises from the fact that we can't solve these problems, and yet we have to figure out how real systems with real fluids in them work so that we can build things, right? Like plumbing systems and rockets and airplanes and so forth. So that's why fluids is an engineering discipline and not a physics discipline, is because the entire collection of basically workarounds, various ways to solve fluid mechanics problems without being able to directly solve the Navier-Stokes equations, that's what we do as mechanical engineers. So basically the entire course of fluid mechanics is just a bunch of cheats, right? A bunch of hacks, because we can't solve the Navier-Stokes equation. So it's important to recognize that everything you guys see in fluids is basically a workaround because we don't know how to solve these problems. And so that leads us to the things that I think that mechanical and aerospace engineers, having taken an undergraduate mechanical engineering fluids class, should know. And I'm going to talk about these in the subsequent fluids refreshers. So we're going to talk about the definition of viscosity. We're going to talk about special solutions to Navier Stokes, all the different incarnations of the Reynolds transport theorem, and the Darcy-Weisbach equation, which ultimately gets you to how to determine the pressure loss in a pipe. Okay, so thank you for your attention for that first fluids refresher. We'll wrap it up there, and I hope to see you in the next one. Thanks.